In 2022, the most expensive telescope ever built opened its eye and almost immediately saw something that was not supposed to be there. Galaxies. Big, bright, fully formed, shining from an era when the universe should have had almost nothing to show. The James Webb Space Telescope launched on December 25, 2021, and unfolded itself 1.5 million kilometers from Earth. Its gold-coated mirror spans 6.5 meters, built from 18 hexagonal segments, shielded from the sun by a screen the size of a tennis court. It cost roughly $10 billion and took a quarter of a century to build. Webb sees infrared light, and that one detail is everything. As the universe expands, light from distant galaxies gets stretched into longer, redder wavelengths. The farther away the galaxy, the more its light is stretched. Astronomers call this redshift, and it works like a timestamp printed on every photon that arrives at the mirror. And because light takes time to travel, every deep image is a photograph of the past. Look far enough out, and you're not seeing the universe as it is. You're seeing it as it was billions of years ago. Webb was built to look further back in time than any machine humans have ever made. Here is the timeline it was sent to explore. The Big Bang, 13.8 billion years ago. For the first 380,000 years, the universe was a glowing fog too hot for atoms to hold together. Then it cooled, the fog cleared, and everything went dark. No stars, no galaxies, just spreading clouds of hydrogen. Astronomers call this the cosmic dark ages. Somewhere in the first few hundred million years, gravity slowly pulled that gas into knots, and the first stars ignited. The models said small, clumsy proto-galaxies would follow, dim fragments, a few million stars each, gradually merging into real galaxies over the next billion years. Growth was supposed to be slow, hierarchical, and faint at the start. Before Webb, the deepest reliable sighting was a galaxy called Gen Z11, caught by the Hubble Space Telescope at redshift 11, about 400 million years after the Big Bang. It sat at the absolute physical limit of what Hubble could do. Finding anything earlier required a bigger mirror and colder, redder eyes. Webb blew past that limit within months of switching on. In its first year, Webb's deep surveys, JADES and CRS, began turning up candidate galaxies at redshift 12, 13, 14. And they were not the dim specks the models had promised. Many were startlingly luminous, as if the early universe had somehow skipped its awkward childhood entirely. A word of honesty here, because it matters. A first detection is usually photometric, an educated guess from a galaxy's colors, and guesses can fail. One early candidate that made headlines at redshift 16 turned out, under the spectrograph, to be a dusty imposter less than a third that far away. Extraordinary claims needed spectra, so Webb took spectra. In 2024, the spectrograph delivered. A galaxy called JADES, GS, Z14-0 was confirmed at redshift 14.3. We see it as it was roughly 290 million years after the Big Bang, when the universe was about 2% of its current age. This was no longer a candidate. It was a measurement. And it is not a speck. JADES GS Z14-0 stretches about 1,600 light-years across, and its starlight adds up to hundreds of millions of suns' worth of stellar mass. Follow-up observations with the ALMA array even detected oxygen, an element forged inside stars. Whole generations of stars had already been born, burned, and died inside it. The record did not stand for long. In 2025, another spectroscopically confirmed galaxy pushed the frontier to roughly 280 million years after the Big Bang. Each time Webb looks deeper, the same message comes back. Galaxies were forming earlier, faster, and brighter than our best models said was possible. Then things got stranger. In 2023, researchers reported 6 candidate galaxies from around 500 to 700 million years after the Big Bang that looked absurdly massive, the most extreme appearing to hold as many stars as today's entire Milky Way. The press called them universe breakers because in the standard model, there simply had not been enough time to build them. But science corrected itself in real time, and this part of the story is just as important. Follow-up spectra showed some of those impossible masses were inflated. Part of the light was coming not from stars, but from hot, glowing gas around feeding black holes. The galaxies were still surprising. They were no longer physics-breaking. That follow-up work uncovered a brand new mystery, the little red dots. Webb keeps finding tiny, compact, intensely red objects scattered across the early universe in numbers nobody predicted. The leading hypothesis, and it is a hypothesis, is that many of them are young supermassive black holes, feeding hard behind thick veils of gas and dust. The black holes are a puzzle in their own right. One object called UHC-1, magnified by a gravitational lens and caught in X-rays, hosts a black hole seen just 470 million years after the Big Bang, already weighing tens of millions of suns, comparable to all the stars of its host galaxy combined. Growing that big, that fast, strains every standard growth model we have. One proposed answer is that black holes did not all start small. Instead of growing from the corpses of dead stars, some may have been born as heavy seeds, giant clouds of primordial gas collapsing directly into black holes of tens of thousands of solar masses. UHC-1's oversized heart fits that picture well. It remains unproven, and Webb is actively hunting for more cases. So, did Webb break the Big Bang? No, and it is worth being precise about what is actually under stress. The evidence for a hot, dense beginning, the cosmic microwave background, the abundances of the lightest elements, the expansion of space itself, is untouched. What is cracking is something one level down, our model of how quickly galaxies can grow. The first fix on the table is efficiency. In today's universe, star formation is wasteful. Most gas never becomes stars because newborn stars blast their nurseries apart. In the denser early universe, gas may have collapsed in intense, rapid bursts that outran that feedback, converting far more of each cloud into stars while the cosmos was young. The second fix: the first stars may simply have been different, forming from pristine hydrogen and helium, with no heavier elements to cool the gas. They could have grown far more massive and more luminous than stars born today. If early galaxies shine with light like that, they need fewer stars to look this bright, and their true masses shrink back toward what the models allow. The third fix is dust. Young galaxies may have made less of it, or blown it out of the way with violent stellar winds, letting far more ultraviolet light escape toward our telescopes. None of these ideas excludes the others, and the honest answer, the one working cosmologists give, is that several of them are probably true at once. Whichever combination wins, one conclusion already feels historic. The universe grew up faster than we thought. Structure, starlight, heavy elements, giant black holes, all of it assembled within a few 100 million years of the beginning. The first chapter of cosmic history is being rewritten right now, in real time, while the telescope keeps staring. And the tools are only getting sharper. Webb spectrographs are stacking up confirmed galaxies at the frontier. ALMA is tracing oxygen and carbon in objects seen barely 300 million years after the Big Bang. NASA's next flagship, the Roman Space Telescope, will scan areas of sky 100 times wider than Webb can, hunting for the rarest, earliest monsters of all. This is exactly what the telescope was built for. Not to confirm what we already knew, but to find the precise place where our knowledge bends. So here is the question worth sitting with. If galaxies lit up this fast, how early could the first planets have formed? And how early could chemistry have started experimenting with life? Tell me what you think below.